All right, hello again. So we're continuing to discuss this particle model of thermal energy. In the last recording, just kind of briefly trying to introduce some of the ideas of thermal energy related to random motions of particles, but we saw that in solids or liquids, it's a little bit complicated because we have to consider these random uh, oscillations, so which have two forms of energy, potential energy and kinetic energy, where in gases we only needed to consider kinetic energy. Okay, so let's start with our model of a solid. So when there are oscillations happening, you can think about each atom being connected to three springs. So why three springs? Well, our solid lives in a three-dimensional world, so we're assuming three-dimensional structures. And when you think about a random motion of this particular atom, it can either move in these three dimensions. So it can move in the, let's call that X, Y, and Z direction, or any combinations of, but the X, Y, and Z are these three independent dimensions. So you have to be careful here. These springs that are drawn here do not represent our bonds that we described when we talked about the particle model of bond energy. These springs really represent these random oscillations now, or the springs that give us rise to these random vibrations or oscillations. So you're not thinking about this as kind of the bond to its neighbor, but each of these atoms are now, we're looking at them as almost independent atoms that vibrate in these three different directions, or any combinations of three. So now in each of these dimensions, as this particle, because again, we're talking about solids or liquids, so there are bonds present, but now we're just thinking about the random motion associated with them. We're only thinking about thermal energy, so we're kind of forgetting about bond energy right now, because as we add energy to the system, we're focused on that thermal energy that changes its temperature, and bond energy is staying fixed. So each dimension then has both kinetic and potential energy because of the interaction. So we have three dimensions, and each dimension has these two types of energy. So what we're actually thinking about is this idea of how energy is stored. So if we were to add an energy to this atom, this idea of what's called equipartition of energy is that energy will equally get distributed between the different ways that each particle can have energy. So what are, again, those different ways? Well, it can have kinetic or potential energy, and we already discussed this, like for a spring mass system, when we add energy to that system, half of that energy goes to kinetic and half of it to potential. So this is that idea of equipartition. It's equally distributing itself among these different modes. We call it modes or ways of having energy. So in this case, for our three-dimensional solid, it's not only potential or kinetic energy that matters, but it also matters the direction. So the dimension. So it could either have all that energy can either be kinetic potential energy in the X, Y, or Z direction, and the equipartition of energy tells us that each type of energy will get, or each type of energy will get the same amount of energy when we add it. So there's basically 6 ways where this energy can go. It can go into the kinetic energy in the X direction, potential energy in the X direction, then Y and Z. So we call those modes. So there's 6 ways to store this energy, and equipartition tells us that on average, each of these 6 ways will get that same amount of energy. So in other words, just kind of thinking about intuitively, if you were to kind of add energy to this one atom, there's nothing about it that says that all the energy should go in the X direction and it should be only kinetic. or in the Y. On average, randomly speaking, it will each way that it can store energy will get about the same amount of energy. So again, we're not talking about nearest bonds or anything. We're just thinking now about each atom being an individual, which is able to have these random vibrations in three-dimensional space. Okay, so moving on, what we say now is that there's some thermal energy associated with each mode. Mode, again, is a way that an energy can be stored. If you are reading some other physics textbooks, another way that this is commonly called is a degree of freedom. So we'll refer to it as mode in 7a, but sometimes you might see degree of freedom. So on average, each one of these modes or degree of freedoms gets this amount of thermal energy. It's equal to 1/2 kb. Kb is a Boltzmann's constant, so it's just a constant, and temperature. So it's proportional to temperature. So again, this is the amount of thermal energy that each mode will get. And this is known as equipartition of energy because, again, each mode will get that same amount of energy, 1/2 kBt. Now, gases and solids will be different because we know that in solids, there's kinetic and potential energy, where in gases, it's all kinetic. So we can already see that, yes, each mode will get the same amount of thermal energy, but there will be less modes because none of that energy will go to potential energy in gases. So we'll look at this in a little bit more detail next. Okay, so let's start with our solid and liquid. Every atom can move in three directions. So there's this three kinetic vibrational modes. We just call them vibrational to stress the fact that it comes from these random vibrations that happen in a solid or a liquid. Plus there's these three potential energy. So for every kinetic mode, vibrational mode, there has to be a potential energy. You cannot have, a spring mass just moving without having potential energy. So there's 3 and 3, a total of 6 modes. So that means that the thermal energy, and then each mode has that factor of 1/2 kBt, but there's 6 modes, so each particle in a solid or liquid will have 6 times 1/2 kBt worth of thermal energy. But that's just one particle. So later we'll think about, well, if we have a mole of particles, our macroscopic system, how do we describe the total thermal energy that system has in terms of these different ways that this energy can distribute itself, modes, in other words. Okay, what about for a gas, and specifically monatomic gas? So this seems a bit subtle at this point. So far, in fact, when we've been talking about gases, we've been focusing on monatomic. Monatomic just means that they consist on one atom. So a bunch of, let's say, hydrogen atoms floating around. But if we're talking about H2 gas or O2 gas, now we have a diatomic gas because each particle now consists of a molecule, and those molecules are bound. So we'll talk about that in a little bit more detail later. But in that case, we have potential energy again. So far when we've been talking about that gases only have kinetic energy, we really meant monatomic gases, because the only thing that type of energy they have is this energy due to their motion. So there are 3 only kinetic energy translational modes. Translational, it just means it's a type of kinetic energy where things are just translating in space, compared to rotational, which will become important shortly for our diatomic gases and so on. Okay, so then there's no potential energy modes. There are no bonds present here in a gas, so no springs associated with any of the interactions. So in that case, when we're talking about the amount of thermal energy each gas particle has, monatomic gas particle, that's 3 times 1/2 kBt, because now there are only 3 modes compared to 6 that each particle. All right, so there's kind of a nice analogy that might help you think about equipartition of energy in these modes. So you could think about it in terms of rain gauges. So what are rain gauges? They're these little buckets that collect rain that give you some information about, let's say, the amount of inches of rain that it rained in a specific period. So you have a bunch of buckets collecting rain, and you can think about these buckets or our modes that we've discussed in terms of these buckets. So if you're adding energy to your solid or liquid, there's these modes where that energy can go, and each mode will get the same amount of energy, the same way each rain gauge will get the same amount of range. So there's nothing, when it's raining and you have these buckets in a field, there's nothing that will, this water will get more or less evenly distributed among these buckets, rather than all the water collecting in one particular bucket. The same idea with equipartition of energy. You add energy to a solid system, solid or liquid or gas. There are different ways that our system can have this energy, and that energy will get distributed evenly. So solid or liquid, there's 6 different modes for each particle. So each row here represents an atom within our solid or liquid. So for each one of those atoms, there are 3 kinetic energy modes and 3 potential energy modes that have to do with those random vibrations. So this is, let's say, atom 1 in our solid, atom 2, and so on. So if we're thinking about, all the way to n atoms. So if we're thinking about n number of modes and how much thermal energy, or n number of particles and how much thermal energy does the whole solid have, not just one particle, what do you have to do? You have to count this total number of buckets and multiply it by this factor of 1/2 kBt. So how do we count this total number of buckets? Well, we have to first know how many modes per atom. So if we're talking about solids or liquids, that's 6. If we're talking about monatomic gases, that's 3. And we'll look at other more complicated gases later. So more generally, we write this as total number of modes per particle. So again, 6 for gas. And then if we want to count all the buckets, we have to multiply by the number of particles. So the total number of particles times the total number of modes per particle, this product will give us the total number of modes present in our system. And then each mode has that factor of 1/2 kBt. So this is our total thermal energy for our system. So again, you can think about energy analogously as this rain, which is coming down, and each bucket fills up with that same amount of rain, which is given by this factor. So you can kind of think about the area of the bucket as being 1/2 kb, which is this constant. Our bucket, the size of the bucket stays the same, but what's different, depending on how much energy you have added, is how much water each bucket gets, or how much energy does each mode get, and that's proportional to the temperature. So you could kind of think about temperature is the amount of energy that goes to each one of these different ways that our system can have energy, or which we call mode, or sometimes it's called degree of freedom. Okay, so let's kind of apply these ideas and combine them with this idea of like total thermal energy, and what does it mean in terms of temperature and so on. So I'll ask you a couple of questions. So first question here, which will have a larger increase in temperature, 1 mole over solid or 2 moles over monatomic gas, if the same amount of energy is added? So let's kind of translate this question. Let's go back one slide. basically what it's asking, if we had 1 mole of a solid or 2 moles of a monatomic gas, and we added the same amount of energy, which one will have a bigger increase in or bigger rain analogously, or bigger temperature here, bigger increase in temperature? Because let's assume that initially we already have some temperature, or the buckets are already full with something. Now we add the same amount of energy to these two different systems. Which one will get more energy per mode or per rain gauge? Okay, so think about it in terms of this equation and how it applies to 1 mole of a solid versus 2 moles of a monatomic gas. Pause the video, think about it. Okay, let's look at the answer. The answer is going to be the same increase for both. So why is that? So for solid, the change in E thermal, so we're just taking this E thermal and saying, we're talking about the change because we're adding energy. So the only thing, the number of particle doesn't change, the moles per particle doesn't change. So that's going to be proportional to the change of temperature. And that's exactly the question, which one will have bigger or smaller change of temperature? Okay, so for the solid, we have 1 mole. So that's the number of particles. That's what goes in here. How many moles per particle? 6, because that's our solid, times this 1/2 kBt. The 6 and the 1/2 cancel, so we have 3 Na kb delta T. For the gas, now we have 2 moles, so we have 2 here, but then instead of 6, we have 3 modes because there's no potential energy modes, same factor of 1/2 kBt. So now you get this 2 and 2 cancels, so we're still left with this factor of 3 Na kBt. So you see that if the change in E thermal, if we're adding the same amount of temperature because this or energy, because this prefactor is the same, they will have the same increase in temperature. So in a sense, if we go back to this analogy, what was the difference? The solid had 6 buckets in each row, but it had half as many rows because we had half as many number of particles, where the gas had only 3 buckets per row, but double the amount of buckets or the amount of rows. So when you multiply the 2 particles times moles per particle, you got the same answer. So that means that the total number of buckets present was the same, so each bucket would get the same amount of rain. If we had half the number of buckets, same amount of rain coming down, then each bucket will get and of course the point here with this analogy is that all the rain has to go into one of the buckets. So it's not like some rain is going somewhere outside. All the energy out to the system has to go to the energy of that substance. So if we had half the buckets, each bucket would get double the amount of energy. But here we had the same amount. So the answer is same. Okay, let's now look at another type of gas. So I've already kind of mentioned that that's what was coming. And specifically a diatomic gas. So what's a diatomic gas? Something like O2 or N2 gas, where you have, let's say, 2 oxygen atoms or 2 nitrogen atoms, or sometimes, CO, well, there's CO2, that's triatomic, but you might have 2 different atoms. Okay, so regardless of what type of atoms you have, what makes diatomic gas special, now what makes it, first of all, a gas, is that now you have molecules which are still flying around randomly. So that means that any molecule is not interacting with another molecule, but there are interactions within that molecule because it's now a molecule, so there's a bond present there. So we still have the 3 kinetic energy translational modes, which means that if we just look at the molecule as a whole, as our particle, that's moving randomly in our 3 dimensions. But also, where else could this energy go when you add energy? This particle now can also rotate, or this molecule, I mean. And specifically, there's 2 ways that it can rotate. So if you take it like this and you rotate it this way, that's one way. Or if you rotate it this way, that's another way. Now, if you take this molecule and you try to rotate it this way, you could think like, well, shouldn't there be three ways or three axes about which it can rotate? And it just turns out that there's very little energy associated with that rotation. The way you can think about it is if that rotation doesn't make a difference, like you can't tell if you take it, if it's a symmetric rotation, because if you take it and you rotate it that way and you were to snap a bunch of pictures, they would all look the same. So that's what we call a symmetric rotation. If it looks the same, then it doesn't count. So this is the reason why we just had one atom. We didn't include any rotational energy, because if we would just rotate in any direction, it looks the same. It's just a ball. Or, we model it as a ball. Where here, if you're rotating in this way at some later time, if you were to take a picture, it would be at a different angle. So they would look different. So for, you don't need to really understand all the kind of details. It's a little bit more complicated of why exactly we only count these two rotational modes. But what you really have to remember, any rotations that do not contain this rotational symmetry count. So when it's a diatomic gas, you only have these two rotational modes. So there's two ways that this energy can be stored in rotations. But also there's this bond between them. So now we have also vibrational mode, because now they're bound and this bond is not being broken. So when you add energy, some of it can go into just moving this whole molecule as a whole faster. Some of it might go into rotating it, and then again some of it, and all based on equipartition, kind of equal amount, will go into vibrating this molecule. But remember, whenever we have vibrations, we have both kinetic and potential energy associated with it. So for this molecule, it's a kind of you can think about it as a 1D molecule with two atoms in a spring. There's one way that it can have kinetic energy, and then thus one way or one dimension where it can have a vibration, which is associated with one vibrational kinetic energy mode and one potential vibration mode. So again, this is associated with this atom-atom interaction. Okay, so we're introducing here a bunch of different types of modes. If we were to count them, that's 5 plus 2, 7 total number of possible modes. So then for our diatomic gas, if we're thinking about, that going back to our rain gauge analogy, each row now has 7 buckets. So the thermal energy for each particle will be 7 times 1/2 kBt. Now there's one subtlety that will come up quite a bit that you need to know about, that sometimes at some lower temperatures, and lower temperatures are even typically like room temperatures, the vibrational modes are not active. What does that mean? It just means that it's a quantum mechanical phenomena that you don't, again, really need to worry about the details of it, but all you have to kind of know is that at those temperatures, those modes are not active. There's not enough energy to activate them. So when you add energy, if you're at a lower temperature and you're adding energy, that energy can only go into the translational modes and the rotational modes. This is known as the freezing out of modes, again, associated with the fact that at some low temperatures, some modes are not active. We will look a little bit more deeply into this in the next recording. Okay, so here's kind of a table that summarizes what we have learned so far. We saw that for solids, there's 3 kinetic energy modes and 3 potential energy modes. Those are due to vibrations, so that's a total of 6. Same for liquids. We treat solids and liquids the same. Monoatomic gases only have kinetic energy modes. Also, careful here, look, this is all the same column. These kinetic energy modes are your vibrational kinetic energy modes, where for the monoatomic gases, we're talking about translational. So this is kind of an average kinetic energy as the particles are vibrating, and this is just your regular motion kinetic energy. So monatomic gases only have those 3 modes, so a total of 3. Diatomic gases at temperatures where the vibrations are frozen will have 5. And then at higher temperatures, there's going to be also, so this 3 is the translational kinetic energy plus the rotational. When the vibrational modes are not frozen, we also have 1 kinetic energy vibrational and 1 potential with which gives us a total of 7 possible modes you can have. Okay, so let's now apply some of these ideas to a couple of questions. So here's kind of a table to remind you about the different mode counts. And this first question asks you, does it take more or less energy to raise the temperature of 1 mole of a diatomic gas versus a monatomic gas by the same amount? So the goal is we want to raise the temperature of these 2 substances by the same amount. The question is which one will require more energy, or maybe it will require the same amount. And just remember, we have the same amount of each gas, 1 mole. All right, so think about this. Think about in terms of how thermal energy is connected to temperature in terms of this ideas of modes. Okay, so it turns out that it will take more energy to increase the temperature of a diatomic gas. So why is that? Well, thermal energy, remember, is proportional to that number of moles per particle. Since we have the same total number of particles, this Na is fixed or the same between the 2 gases. So the only difference would be the total number of modes per particle. And for diatomic gases, whether vibrational modes are active or not, you have more modes. So either 5 or 7 versus 3. So what that tells us is to have the same delta T, you will have to add more energy. So bigger change in E thermal. So in a sense, you can think about it because there are more total number of these buckets, going back to a rain gauge analogy, when you, if you want to fill up each bucket by the same amount, you would need to have more rain when you have more buckets. Okay, a slightly different question now. If 1 mole of a diatomic gas and 1 mole of a monatomic gas are placed in an insulated container and are allowed to reach equilibrium, so now we have these 2 gases, we put them together, we're assuming they're initially at different temperatures and they're coming to a thermal equilibrium. Which one has a greater change in temperature? So here you have to kind of remember, go back to your ideas of thermal equilibrium and conservation of energy and how does it apply to this system, and now connect it to this modes, or thermal energy being proportional to number of modes. Okay, so let's pause the video, think about this. Let's take a look. So in this case, the monatomic gas is the answer, will have a greater change in temperature. So let's think about it. So in this situation, what is the same? Here, the change in E thermal is the same. So why is that? We have an insulated container. What is conservation of energy tells us is that as they come to thermal equilibrium, whatever heat one is losing, the other one has to gain. So whatever change in thermal energy one gas has, it has to be equal and opposite to the change of thermal energy of the other gas because it's a closed system. So here we only care about the magnitude. So what it's telling us is that the magnitude in the change of the thermal energy of the monatomic gas has to equal to the one of the diatomic gas. And now if we write these in terms of this modes, we can see that, okay, the constants up front cancel because they're going to be the same, like the 1/2 kBt, or the number of moles because both of them have 1 mole for both gases. So what we're asking here is which one will have a greater delta T? Well, the monatomic gas has less modes, so we put 3 here. And let's say vibrational modes are not active. So we put 5 or 7, it doesn't matter, you'll get the same answer. If we were to put 5 here and 3 here, for these two quantities to be equal, this delta T has to be bigger because it's multiplied by a smaller number. So what that tells us is that the monatomic gas will have a larger change in temperature. Let's look at this in terms of our rain analogy. So again, when only two things are allowed to exchange energy, each one of them will get the same amount. So it's not really a direct analogy. It's more like rain is being, it's more like you're pouring the same amount of rain from here to here. You're not adding rain to both, but because we're really only care about magnitude, let's just, for simplicity, think about adding. So we're adding the same amount of rain to each system, but for monatomic gas, we only have 3 buckets per atom, where we have, let's say, when there are no vibrational modes, 5 for diatomic gas. So if we added the same amount of rain, then each bucket here will get more water than each bucket here, just because we have less buckets. So more water per bucket. More water per bucket translates to our physical system. Here we're talking about to more temperature, because remember, this kind of, in this analogy, the amount of water in each bucket is proportional to temperature. So this is here showing that our monatomic gas will have a bigger change in temperature. So more modes, less energy per atom. All right, I think that's it for today. So just to kind of preview what's coming up next. So what have we done so far at this point? All right, here, I wanted to go back here. We defined the thermal energy in terms of these modes. How many modes each particle can have, how many particles we have, and then this prefactor. But this kind of should already look familiar, because back in the beginning of the course, we also had a definition for thermal energy, but we did it in terms of heat capacity or specific heat and the amount of substance we had. So we had an equation that related thermal energy to temperature. So what we're going to do next is, now we have these two different ways of defining temperature or thermal energy and its relationship to temperature. So that will allow us to make that connection between this idea of what we defined as heat capacity or specific heat, and which was a macroscopic quantity, to this macroscopic understanding of how energy is stored through modes. So that's what's going to be coming up next. All right. Thank you for listening. See you next time.